Hi guys. Today what we're going to talk about is we're going to talk about separable differential equations. The other day I had a couple of friends over and we were sitting out on the front porch, and my friend Patty, she brought us over some cornbread. And believe it or not, at the time I was thinking about how I'm going to do this video and what I'm going to talk about, and I was looking down at the cornbread. We were out there having some tea and cornbread, and I had just dawned on me Newton's law of cooling. And so that's what I'm going to kind of talk about today. So I'm going to talk about separable differential equations in terms of cornbread. So basically, before we do that, we should talk in general about what differential equations are. So differential equations can take the forms that we have here, these three forms. So we have these three forms here. And a solution to a differential equation has to be a function or a class of functions. And the functions are considered to be dependent variables, while the variables x, y, and z are considered to be independent variables. So let's go down a bit here. And so here's a little example if you wanted to work it out. And you can use that first form there, and it would meet the condition. So, but let's now get to our cornbread here. So in dealing with cornbread, we will kind of want to think about what Newton's law of cooling really says. So Newton's law of cooling says is that there's going to be a change in the temperature over time. And that's going to be directly proportional to the object temperature minus the ambient temperature. Now, if you'll notice here, there's a formula here which says times negative k. Well, you're going to have that k constant in the formula, but the negative value on that constant is really just showing us that the cornbread's going to cool over time, especially that we're sitting out on the porch and stuff to eventually reach that ambient temperature. So how do we figure this out? How do we do separable differential equations? And if we go to page 331 of the text, 7.3, it kind of shows us this formula here. So what we can do then is we can divide by the object temperature minus the ambient temperature, and we'd get these two equations here. And then from here we can integrate both sides. So what we get is we get the natural log of the object temperature minus the ambient temperature, and that's gonna, and then on the other side we're gonna integrate towards t. Okay, so what we're going to end up getting is the negative k, but integrating with t, we're going to get negative kt. Now, if we raise each side to the to e, to the engineering e, what we're going to end up getting is we're going to get the absolute value of the object temperature minus the ambient temperature is going to be equal to e to the negative kt plus c. And that simplifies down to the form that's under it, which is right here. So the bottom line here is that we can use this formula, to determine, how the the cornbread, I mean, strange topic, but it's kind of what we were doing at the time, how the cornbread is going to cool over time. So when the object is hotter than the ambient temperature, we can write forms. So what we can do is we can say when the object is greater than or equal to the ambient temperature, we get this form here. And now if the object temperature is less than the ambient temperature, assume we ate some of the cornbread and then decided to put the remainder in the refrigerator, and later in the evening we pulled it out, then we'd get this form here. Okay. Now there's some good videos on YouTube that shows you how to crank this formula. So if you just do that, and you can also, I'm sure there is some too. Oh, I know there is actually on Kahn Academy as well. So that would do this as well. So okay, so that's it, guys. So that's a little bit of cornbread and and a little bit of Newton's law of cooling. And thanks so much, guys. Bye now.